Hello and welcome to another lecture on Generating Functionology by Herbert Wilf. My name is Hunter Ream, and I'm going to be talking about section 2.1 today on formal power series. Now up until this point, we've been defining power series and using power series, but now is really when we're going to formalize them, for lack of a better term. So first off, let's define what a formal power series is. A formal power series is an expression of the form a sub 0 plus a sub 1x plus a sub 2x squared, and so on. So really it is just an infinite polynomial, a power series. It's really what it is, where the sequence a sub n is called the sequence of coefficients. The sequence of coefficients. Now our goal is really going to be to take these objects. Now for any sequence we can define a formal power series, and what we really want to do is we want to create a ring out of these. And if you don't know what a ring is, it's no big deal. Really the first thing that we need to do is we need to define the operations. We want to be able to add these things, subtract them, multiply them. And so let's start out first by taking or recognizing that this operation will do. If we have this power series and another one, let's say with bn's, then if we add or subtract them, then we just simply do that to the corresponding terms. In other words, we combine like terms, just as you would if you were just given two polynomials and were told to add them together. And we're also going to be using the same operation that we would use with polynomials for multiplication. So I'm going to use this dot to represent the multiplication, but if we wanted to multiply two power series, then we want to be able to get another power series, and I'm going to denote it by Cn. So sorry, the corresponding sequence is going to be denoted by Cn here, and where Cn is going to be the collection. We're going to be defining Cn to be the collection of corresponding. Essentially we're going to be collecting like terms, and what this comes down to being is Cn ends up being k equals 0 up to n of ak b n minus k. And what's the intuition behind this? This almost seems a little random, but it's not. The point is that if we focus just on, here I'll grab my laser pointer, if we focus on this ak, then we know for a fact that just the ak is going to be the coefficient on some x to the k. And b, n minus k, well certainly that's the coefficient on some x to the n minus k. So when I multiply the two, the corresponding x value that would be next to it would be x to the k times x to the n minus k, which would, you can just add the exponents to get, well, the coefficient. This is going to be the coefficient on an x to the n, and that's what we want. We want the coefficient on x to the n. So this actually makes sense. And this is carried over from just multiplying polynomials. So here's an an example, in some ways this is an example, and it's suggestive of the next point that we're going to be talking about. But by the geometric series, formula, which we use quite often, we know that 1 plus x squared plus ... well, that's going to be equal to 1 over 1 minus x. Here, I'm going to move that a little more central. But if we multiply the 1 over x over to we'll multiply by 1 minus x on both sides. I'll put this in parentheses now. The 1 plus x squared plus ... Well, this is going to be equal to 1. So when I multiply these two together, which it seems that the first one, this 1 minus x, that is actually a power series where all of the other coefficients that aren't listed are just 0. And this is a power series where all the coefficients are just 1. So if I multiply these two power series together, indeed we get 1. So this is suggestive of having inverses in some ways. Now, I say inverses because maybe that's what we're used to hearing, but in reality what this is for us, we're going to be calling it the reciprocal. I will state that this is an example, of a reciprocal, which is a word that we've heard, and it almost seems, that I shouldn't be specifying that it's reciprocal. Like, why can't we just call it the inverse? Well, we can, but there's a small difference between the inverse and the reciprocal in this case because we're dealing with functions. When we talk about functions and inverses of functions, we normally mean under composition. And in this case, we're not composing any functions, we're actually multiplying them. So we're going to be using the word reciprocal in this case because we're dealing with functions. Now let's move on to our first proposition. I'm going to go to the next page here, and I'm just going to make sure I'm at the top here. Yeah, so here is a proposition. So a formal power series f, which will be equal to the sum from n equals 0 up to infinity of a n x to the n, so it's just a normal power series with coefficients a n, has a reciprocal if and only if a sub 0 is not equal to 0. And the proof goes something like this. So let's do the first direction. Suppose f, which is defined above, but I'll write it again, has a reciprocal and we'll call it, again, suggestively, 1 over f, which is going to be equal to the sum from n, let's try that again, n equals 0 up to infinity of bn x to the n, right? And so let's just say that these two are reciprocals of each other. Then, certainly, by the definition of being a reciprocal, we know that the product of them is going to be 1. And so, if we just think about what it means for two power series to be actually equal, it really means that their coefficients are equal. And so, in particular, their constant terms are going to be identically equal. So, if I multiplied f times 1 minus f, its constant term has to be a0, b0. And this is going to have to be equal to 1. Because the constant term on the right-hand side over here, well, it's a 1, right? And so it has to be 1, so this product has to be 1. And this immediately implies, by what we know, that, and I should say we're working in a space where we don't have zero divisors, so thus a0 is going to be not equal to 0. Now, so that's the one direction. Now we want to assume that a sub 0 is not equal to 0, and this is a second separate argument, right? We assume now that it is not equal to 0, and we want to show that there exists an inverse. Or sorry, a reciprocal. Define, and I won't show this explicitly, but here's what it is. We're going to say define b sub n to be equal to -1 over a0 times k equals 1 to n minus 1 of ak bn minus k. And I won't show this, but this is going to be the sequence that's going to explicitly define the reciprocal. This will generate the reciprocal of f. So that's the end of that. I will say, though, since this construction right here was so explicit right here, was so explicit and defined explicitly in terms of f, so note the reciprocal is actually unique. It is unique. So that's noteworthy. That's noteworthy. We have just unique reciprocals. And maybe we'll call them unique multiplicative inverses. So that was quite fun. But the next thing that we want to define is something that we've also been using up to this point in chapter 1 for sure, is the derivative of these things. We've not worried about convergence and said, hey, sure, we can move this derivative inside and outside of our power series, not even worrying about convergence. But now, let's define it explicitly. Say the derivative of the formal power series let's put one out there, f equal ranging over n of a sub n x to the n is the series f prime, which is equal to, well, really the same as if we were to just differentiate term by term. So n a sub n x to the n is what we defined the derivative here. And so a proposition, one that is kind of cool and sort of predictable in some ways, is that if the derivative is equal to 0, well, we're hoping that it's going to match our intuition about what derivatives are. So if we had a function whose derivative was 0, then we would probably assume that, well, then the original function f would be constant. So let's see if we can prove that. And this is just a one direction, right? The other direction is trivial. But we want to show this. So suppose that that's true, then if we define f to be, the normal a sub n x to the n, then f prime is equal to that, but with an n, and a corresponding n minus 1 as our exponent. Thus, n, an is equal to 0 for all n, right? We claim that this entire thing is equal to 0, so it's all going to be equal to 0. And since this is the case, then it must be the case, thus a sub n must be equal to 0, because certainly n is never equal to 0. And this must be true for all n. So f is constant. The one thing that we should note here is we never at any point said that a sub 0 would be 0. Because the reason that we never said that is because it's not necessary. If we focus on this sum right here, we see that, well, yeah, it starts at 0, so that should be one of the n's that we're considering. But if we say that 0 times a sub 0 equals 0, well, that's true regardless, and we don't actually have to consider that. We can't say definitively that a sub 0 is 0 because it's being multiplied by 0. So that product does not guarantee anything. So, but certainly it'll be constant and it'll be equal to whatever a sub 0 is. All right, and the last thing I want to show here is something that's kind of neat, and it's about the function. So let's say this. So it's a proposition. We'll say if f prime is identically equal to f, and again, these are all power series, then f must be equal to c e to the x. Let's see if we can prove this. And it's just one direction, so so first recognize, since f prime is equal to f, then n plus 1 a sub n, n plus 1 a sub n plus 1 will be equal to a sub n. And the reason this is because when we take the derivative, we actually knock down one of the exponents on the x, so we end up getting this a sub n plus 1 is actually equal to a sub n, but with a coefficient. And this is going to be true for all n greater than or equal to 0. Thus, well, a sub n plus 1 is just equal to a sub n all over n plus 1. By induction, in particular on n, a sub n is just going to be equal to, well, the only one that's going to remain in the numerator is going to be a sub 0, and down below we're going to be multiplying by n each time, so we end up with an n factorial. Thus, we get that f must be equal to well, it was originally equal to this, but we determined that each one is just equal to a sub 0 over n factorial, so let's write that. Which is identically, we can factor out this a sub 0, and that ends up being the power series for e to the x. So this ends up being a sub 0 e to the x, So this a sub 0 is our constant. I mean, I wrote in the proposition that it was c. Could have been more suggestive about that, but we did find some constant that did this for us. So that ends our proof. And that actually ends the section as well. Thank you for listening.